Welcome to the video on the thermodynamics of mixing. So recall that the total Gibbs energy of a binary mixture, so it's a mixture of two different substances, can be given by this equation. So we have the Gibbs energy is equal to the number of moles of component A times the chemical potential of component A plus the number of moles of component B times the chemical potential of component B. And also recall that at constant temperature and, or rather, that at constant temperature and pressure, systems tend towards lower Gibbs energy, which is to say that spontaneous changes lower the Gibbs energy. So for a spontaneous change, this value of G has to be lowering. So now we can examine the thermodynamics of a system as its composition changes spontaneously, like during the mixing of two substances. So we're going to start out by examining the mixing of two gases introduced into the same container. And so we're going to assume here that these gases are ideal to start with. So the mixing process is spontaneous. We know that this is spontaneous. If we put the two gases together, they will spontaneously mix together. And therefore, we know that that mixing process has to correspond to a decrease in Gibbs energy. Right? So our G has to decrease. So suppose we have amounts Na and Nb, so Na and B are some number of moles of two ideal gases at a temperature T and a pressure P, with the gases in two separate containers. So we have a case like what we have up here. So we have some number of moles Na at a temperature and pressure T and P respectively in this side, and we have some other number of moles in B at the same temperature and pressure over there. So we've got the yellow side and the blue side. Now the chemical potentials of the two gases are the chemical potentials of the pure gases, because they are pure. In this case, we haven't mixed them yet, right? So before we mix them, the chemical potential of A is the chemical potential of the pure gas, and the chemical potential of B is the chemical potential for the pure gas. Then we're going to mix them. We're going to mix the A and B together down here, still at the same temperature and pressure. So recall that the molar Gibbs energy of at some final pressure, so PF, is equal to the standard molar Gibbs energy at our initial pressure plus RT times the natural log of our ratio of final pressure to initial pressure, the standard P naught. And also that the definition of chemical potential, mu, is the molar Gibbs energy. So now this is the chemical potential at that pressure. So that means that the chemical potential is equal to the chemical potential at our initial value, our standard conditions, plus RT times the natural log of the ratio of our two pressures. Right? So here the P naught is the same pressure that our chemical potential reference is at. So the mu naught is the standard chemical potential. That's the chemical potential of our pure gas at 1 bar. So the P naught here is 1 bar. So if we constrain ourselves to represent pressure P in terms of bars, then we can say that this ratio, P over P naught, remember that P naught is 1 bar, so that's our pressure in bars. So as long as we're only inputting our pressure here in bars, then because P naught is 1 bar, then P over 1 bar is just P, but now it's unitless. So basically what we're doing here is we're eliminating the units there, but we're constraining ourselves to listing our pressure here by calculating in any calculations that we have. We're listing it in bars, which is close to unitless. So using this constraint, then we can simplify our equation from the last slide to the chemical potential mu is equal to the standard chemical potential at 1 bar plus RT times the natural log of our pressure. And again, that's the pressure in bar. So now the total Gibbs energy of our system before mixing is, so that's the initial Gibbs energy, is the chemical potential of substance A times the number of moles of substance A. Remember, this is pure A at this point because it's before mixing, plus the chemical potential of B times the number of moles of B that we have. And so now we can figure out what these chemical potentials are at any other pressure than 1 bar. So now we still have, from this term, we've expanded that, so we have our number of moles of A, that's not changing, and now we change our chemical potential of A at the pressure that we're looking at to the chemical potential of A at 1 bar, plus RT times natural log of the pressure, again, still in bars. Plus a similar term for our second component B. And so now once the gases mix, then the partial pressures of the gases are PA and PB, where the total pressure now is the sum of the two pressures. That's nothing new. So now, this means that the total Gibbs energy of the mixed gases, so now this is the final Gibbs energy after mixing, is now similar sort of number of moles of A times chemical potential of A at 1 bar, plus R times T times the natural log of the partial pressure of A. Before we didn't have, on the last slide, here we don't have to say the partial pressure of A because the two gases are at the same pressure, so they're each occupying whatever volume they're going to occupy, but the pressures of the two are equal. But now, after mixing, the partial pressure of A isn't the same value it was before. It's something less, because now it occupies a larger volume. So now we have to have the partial pressure of A here, and then similarly the partial pressure of B over in the expression for B. And so now the change in Gibbs energy for this process is the Gibbs energy of mixing, right? That's the delta mix G. So the Gibbs energy of mixing is the final Gibbs energy minus the initial Gibbs energy. Well, here's the final Gibbs energy minus the initial Gibbs energy that we had. And so again, note that we have similar sorts of a similar sort of setup. We have Na times this quantity and Na times that quantity. Only note here that the only difference is that we've changed from the initial part. We have our pressure. We're not differentiating between the pressure for A and the pressure for B because it's the same value. But afterwards, after mixing, the partial pressure of A is not necessarily the same as the partial pressure of B. It would be the same if we had equal number of moles of A and B that we were mixing. But it doesn't have to be. We don't have to have the same number of moles, so if we don't, then those partial pressures will be different, and so that's what we're taking into account here. So, this means that now we can combine these two terms together and get, and then combine the two terms for B. And so now the change in Gibbs energy of mixing, so the Gibbs energy of mixing, is the number of moles of A times R times T times the natural log of the ratio between the final partial pressure of A and the initial partial pressure of A, plus, similar thing for B, number of moles of B times R times T times the natural log of the ratio between the final partial pressure of B and the initial partial pressure of B. And also recall from Gen Chem that the definition of the mole fraction, chi for some component J, is the number of moles of J divided by the total number of moles. And also recall from Dalton's law of partial pressures that that same value, chi J, is can be found by taking the partial pressure of J divided by the total pressure. And so here P is the total pressure of the system. So over however many components you have. If J is the only thing you have, well, then the partial pressure of J divided by the total pressure is 1, and the mole fraction is 1 because you have pure J. Alright, therefore, now we can simplify our equation for our Gibbs energy of mixing to replace the previous fraction that we have here and there we can now replace these two fractions with the mole fractions. So now we have Gibbs energy mixing is equal to the number of moles of A times R times T times the natural log of the mole fraction of A plus the number of moles of B times R times T times the natural log of the mole fraction of B. And now we can combine the number of moles of A and the number of moles of B, and we know that the total number of moles, N, is equal to the number of moles of A plus the number of moles of B, and we know that chi is equal to the number of moles of A divided by N. So we can do some algebra, and so now we have the Gibbs energy of mixing is equal to N, now the total number of moles, times R times T, times the mole fraction of A times the natural log of the mole fraction of A plus the mole fraction of B times the natural log of the mole fraction of B. So, because the mole fractions are never greater than 1, but they always have to be between 0 and 1, so that means that the logarithms here, this logarithm and that logarithm, they have to be negative, because the natural log of a number less than 1 has to be negative, and that means that the Gibbs energy of mixing has to be less than 0, because if this value is negative and that value is negative, the mole fraction is always between 0 and 1, so that has to be positive. The number of moles is positive, R is positive, temperature is positive, so that means that we have some positive values multiplied by each other times some negative value plus some other negative value. So this value together, this stuff in parentheses, has to be negative. So our Gibbs energy of mixing has to be negative, which means that the Gibbs energy of mixing has to be, if the Gibbs energy of mixing has to be negative, that means that the mixing process has to be spontaneous, which is what we expect. If we mix two gases together, we expect them to mix spontaneously, no matter what their ratios are, no matter what the identity of the gases are. If they're ideal gases, they're going to mix spontaneously. So this means that the gases will mix spontaneously in all proportions. Doesn't matter what proportions we put them in, doesn't matter what the mole fractions are, they're always going to mix spontaneously. So because they'll always mix spontaneously, we can then look at a plot of the Gibbs energy of mixing. So this is actually the Gibbs energy of mixing divided by nRT as a function of mole fraction. So you note here we have, at this point, we have a Gibbs energy of mixing of 0, and over here at this point we have a Gibbs energy of mixing of 0. Well, that just means if we have here the mole fraction is 0, so this is the mole fraction of A, that means that if the mole fraction of A is 0, that means we have a mole fraction of B of 1. So we have pure B. Well, if we have pure B, then the Gibbs energy of mixing is 0, because we're not mixing anything. We have pure B and we're adding no moles of A to it, so it's still pure B. And likewise over here we have pure A. If we add 0 moles of B, we're not going to change the Gibbs energy. But anywhere in between, the Gibbs energy is negative, and so that means that the two gases should mix spontaneously. Also note that down here, at mole fraction of 0.5, we have the minimum, which means that even if we have something right there at, say, 0.45, a mole fraction of 0.45, if we add more of our minor component, it will still be a spontaneous mixing, because we'll still be moving down in our along this this curve. So, right. So, recall that the partial derivative of Gibbs energy with respect to temperature at constant pressure and number of moles is negative entropy, negative S. And this means that for a mixture of ideal gases, initially at the same pressure, then the entropy of mixing, this value delta mix S, is this, right? And so now we know what delta G of mixing is, right? And so now we can go ahead and plug that value in. And so basically we're dividing by the temperature. So we've plugged in our, there should be a negative here. And so now we have negative NR, we've lost the T here because we've divided by temperature. And then we still have our chi mole fraction of A times natural log of mole fraction of B plus mole fraction of A rather, plus the mole fraction of B times the natural log of the mole fraction of B. And so that's the same thing there. So again, because the natural log of our mole fraction is negative, the entropy of mixing has to be positive because now this value is negative for all values of chi. So now we have a negative times a positive times positive times a negative. So now this right side has to be positive. So the entropy of mixing has to be positive. That's good. That's what we wanted. The entropy of change has to be positive. The entropy change as we mix two gases together, we're getting significantly more disorder when we mix a pure gas with another pure gas. So we expect the disorder to go up. So that is in fact what we see. So we see the entropy of mixing divided by N times R here as a function of mole fraction of A. So starting at 0 going to 1. So again, at a mole fraction of A of 1, the entropy of mixing is 0. At a mole fraction of A of 1, the mole fraction, the entropy of mixing is 0. Because again, we're not mixing anything. So it's got to be 0. So, and again, anywhere in between, it's a positive value. So it's always spontaneous to mix two ideal gases. And this means that for equal amounts of gas, we can say that chi A is equal to chi B, and each of them are 1/2. If we have equal amounts of A and B, then we have double the number of moles of A. Of the total number of moles is double the moles of A or double the number of moles of B. And this now means that our entropy of mixing is minus N times R times 1/2. That was the chi A times the natural log of 1/2 chi A plus 1/2, that's chi B, times the natural log of 1/2, that's still chi B. So now we have 1/2 of natural log of 1/2 plus another 1/2. So now we have plus, in parentheses there, we have 1 times the natural log of 1/2. So that's what we have here. So we still have our minus NR times the natural log of 1/2. And now note that we're combining this negative with the natural log there of 1/2, and we're turning that into N times R times the natural log of 2. So if we have equal quantities of A and B, now our entropy of mixing is N times R times the natural log of 2. Right? Where here N is the total number of moles of gas of A and B. So we can now calculate the isothermal isobaric enthalpy of mixing, delta mix H, which is the enthalpy change accompanying our mixing process. And remember that the Gibbs energy is defined, this is the definition, right? Delta G is defined as delta H minus T delta S. And so we can rearrange this, get H on the other side, and so delta H is equal to delta G plus TS, T delta S. And this then means that the enthalpy of mixing at constant temperature and pressure then becomes the enthalpy of mixing is equal to the Gibbs energy of mixing plus the temperature times the entropy of mixing. And so now we know the Gibbs energy of mixing. So this guy is this value. And we know T is the temperature. And now we know the entropy of mixing is the stuff here in brackets. And so now we have nRT times this quantity, stuff with chi's minus nRT times that same quantity. So we have nRT minus nRT times that quantity. Well, that's 0. And so the enthalpy of mixing for ideal gases is 0. So our enthalpy of mixing of ideal gases is 0. This is what we expected for a system in which there are no interactions between molecules in the mixture. Right? They're ideal gases. With ideal gases, we're assuming that because it's ideal, that there are no interactions between the molecules. If there are no interactions between the molecules, then when we bring other molecules close by, there's no energy change because there's no interactions there. Now, for real gases, there will be an enthalpy change because real gases have some attractive or repulsive forces between the molecules, and so this won't be true. But for an ideal gas, it's true. So as long as we're working in conditions where we can treat our gases as ideal, then the enthalpy of mixing will be approximately equal to 0. So this means that the driving force for mixing of ideal gases is entirely from the entropy increase of the system. That is, the entropy of the surroundings don't change because the enthalpy isn't changing. Remember that the enthalpy is equal to is related to the entropy change for the surroundings. So that was the thermodynamics of mixing.